talking about the chain rule. This is a very, very important rule to get a hang of. We also saw a little bit of it before. I just don't think we really paid attention to it because we didn't really have to. So let's talk about it. Chain rule, just as it sounds, means that there's some sort of chain reaction, right? Something happens, and because of that, there's another response to it. What this looks like in differentiation is if we have d over dx of u to the power of a, that's going to equal to a minus 1. Recognize that this is the power rule over dx. But we never actually talked about this part here. What if, instead of just having, say, x cubed and taking the derivative of that to get 3x squared, we had the derivative of x plus 2x cubed? How would we go about this? Well, the power rule tells us that we're going to bring down the exponent, x plus 2x, leave that as it is, take 1 from the 3, which is 2, and now we have to multiply it by the derivative of what's inside the bracket, the original function that we started with, right? So if we actually see this as the rule that we mentioned above, this is the u and the a, right? So we have a minus 1. Now we're multiplying that by u prime, right? U. So we're going to multiply it by the derivative of what's inside the bracket. Well, this is a lot easier now, right? So derivative of x is 1 plus the derivative of 2x, which is plus 2. Seems a little redundant, yes, but just for this sake, we're going to leave it this way. And we can simplify this to get 9x plus 2x squared. Okay, what we notice is that this formula is an application of the chain rule. So we're basically using the power rule to find derivatives of more complex functions. For example, if we have f of x is equal to x squared minus x plus 2, and I ask you to solve for the derivative. Well, this is quite simple, and we've already seen how to do this, right? We would get f prime of x is equal to 2x minus 1. Now, what if the equation was f of x is equal to x squared minus x plus 2 to the power of 4? Right? Now it gets a little more tricky. All you need to remember is you're going to use the power rule and then multiply it by the derivative of what's inside the bracket. That's the chain part, right? You do something and then you have to do something else as a result. So f prime of x in this case, we're bringing down the 4, leave the function as it is in the brackets. I told you brackets are very, very important. Now we do 4 minus 1, which is cubed. This is still the power rule. Now the chain rule comes into play because we're going to have to take this equation and multiply it by the derivative of what's inside the bracket. Well, the derivative of what's inside the bracket, we just did that. That's 2x minus 1. So we're going to multiply that by 2x minus 1. And that is the derivative of x squared minus x plus 2 to the power of 4. And this is pretty much the general case. Okay, let's do another practice problem before we move on. What if we had f of x is equal to x squared plus 10x minus 2 to the power of 3? Again, the derivative of this is going to be 3, which is the power rule, plus 10x minus 2 to the power of 2, still the power rule. We have to leave it as it is first, and only then do we multiply it by what's inside the bracket, the derivative of what's inside the bracket, which is 2x plus 10. And that's it. Not so scary, right? Okay, well, how can we use this in more complicated problems? For example, composite functions, right? So what's a composite function? Well, let's talk about that a little bit. Composite function. If you remember, a composite function looks something like this, or f at g at x. The derivative of composite function is where the chain rule is very, very useful. If, for example, we had x cubed plus 1 to the power of 10, and this is our function. And actually, for this case, I'm going to use y. Composite function just says that we have these two functions being a part of each other, right? So it's like, think about finding the parent function. What I mean by this is, well, we can recognize that we have two things going on. First, we have the case of f at x, say x to the power of 10, right? We have something to the power of 10. And then the second case of g at x, where it is the actual function x cubed plus 1. Now, if I said f at g at x, that means that we're taking the x value to be the actual function g at x. Right, normally, you wouldn't go about a normal function, say if we had f at x is equal to x at 10, as mentioned, and I asked you what's f at 3, well, what would you do? You would simply plug in 3 into the x, and then you would solve. So we get 3 to the power of 10. So it's the same thing over here. All we're doing is we're plugging in the g at x function into the x value for f at x. So we plug in x cubed plus 1 into x and to the power of 10. Being able to identify these functions in cases like this is very important and very, very useful, especially when we want to apply the chain rule. Yeah. So now I'll see you in the next section. We're gonna